So occasionally when you're running through the algebra process, when you're asked to find a certain y value for your function, there ends up being more than one x that returns that particular value on y. Now this happens with four types of functions: the parabola, and then the sine, the cos, and the tan trigonometric functions. Now in the independent study, you've done quite a bit of work on cast rule, etc., for finding those multiple solutions for the trigonometric functions. I will do one here just for completeness. I'm going to go through and do the actual algebra, get the multiple solutions, and then we'll talk about why that's happening. So I'm going to run through this one in the more traditional manner. I'm going to start with my function, 2 times 3 times x plus 4 all squared minus 5. And I want to find the place where that function equals 67. So I have to start peeling things away from this x. That would be the last thing I do to it, so that's the one I'm going to undo first. I undo subtract 5 by adding 5. 67 plus 5 is 72. And that leaves the 2, the 3, the x plus 4, and the squared. Alright, the next thing to undo is a 2. So to undo multiplication by 2, I divide by 2, and 72 divided by 2 is 36. So then I have 3 x plus 4 squared. Next step is to summon the antifunction for square, so 3 times x plus 4. And this is where it gets tricky, this line right here, is that the antifunction for x squared feels like it should be 36, and it is, but not quite. In order to get the proper antifunction pair here, I have to consider both plus and minus. So if this thing squared is 36, then this thing could either be worth, let's see, either it's worth positive 6 or it's worth negative 6. And the reason for that is if I were to square this side, this times itself is 36, this times itself is 36. Both of these situations would end up generating that line. So if I came backwards to that point, I don't know which one of these pathways I started from. So I'm going to have to consider both. What that's ended up doing is generating cases. So I have case 1 over here, and I have case 2 over here. Both of them are valid solutions, so I have to carry on as though both of them are true. So if I finish this case, divide both sides by 3, I get x plus 4 is 2. Kick the 4 over. 2 minus 4 would be negative 2. That's the answer to case 1. Case 2, divide by 3, gives me negative 2. Kick that over. Negative 2 subtract 4 would be negative 6. So if you put either negative 2 or negative 6 in for the x value here, you will get 67 as your output. So to try and convince you about why that's true, if I were to just quickly sketch this very roughly, you may remember that this is a parabola that has been shifted down 5 and to the left 4, so its vertex is somewhere over here. Looks something like that. And what I've asked the algebra is I've asked it, when does this thing have a height of 67? Well, if you scan across, there are 2 locations where that happens. One on the left branch and one on the right branch. And this obviously didn't work out to scale. But you can see that there's one on the left branch, one that is further that way, and one that's on the right branch. So when you do a parabola or any function that has this tendency to turn around, you can have a potential situation where there's multiple solutions. So you can see that's why it happens with trig functions, right? Your trigs start like this and they do that kind of thing. So if you asked when the height was here, it's going to have a solution there and there, and there, and there. And in fact, because the sine function doesn't ever stop, the sines and cosines actually end up generating an infinite set of solutions because of this turning around behavior. Tan is the same, but its graph is kind of wonky. So look it up if you'd like. You can see that it has a repeating pattern that allows multiple solutions to show up. So I'm going to do one sine example just so that it's in this. Sometimes there's more than one answer set. And then I'll set you off to the practice problems. Okay, so here we go. Same traditional method. Start with the function 6 sine of 3 times x minus pi over 2. Subtract 2, and I want to know when this function is worth -5. So I have to kick this thing over by adding 2. So 6 sine of 3 x minus pi over 2 is -5 plus 2 is -3. And I'm going to divide both sides by 6, leaving this behind. -3 divided by 6 is -1/2. I have to summon the antifunction here. The antifunction for sine is arcsine. Looks like that. So this number is either something awful that I have to type into the calculator, or it's a special triangle ratio. If I recognize it as special triangles, then I can use them. If I do not recognize it as special triangles, I'll have to use the calculator and some complicated stuff. But I spot that that is from this particular special triangle, 1, 2, root 3, which has a pi over 3 down here and a pi over 6 up there. For sine ratio of 1/2, the opposite over the hypotenuse would have to be for pi over 6. So this is the pi over 6 family. And cast rule says I'm going to find a negative sine ratio in this quadrant and this quadrant. So the pi over 6 family member in there would be 7 pi over 6 in this quadrant and 11 pi over 6 in that quadrant. So that's one more than a full pi and one less than full 2 pi. So I've got my cases here. 3x minus pi over 2 equals 7 pi over 6, and 3x minus pi over 2 equals 11 pi over 6. And don't forget that this value can be rotated a full circle and still be a proper solution. And then it can be rotated another full circle and another full circle, an arbitrary number of full circles, and you would still get a valid solution. So case 1. Case 2, it turns out not only is there more than one answer, but there's an infinite set of answers under case 1 and another infinite set of answers under case 2. I'm not finished. I don't have it saying x yet, so I have to divide both sides by 3. This divided by 3 would be 7 pi over 18, and this would be 2 pi over 3n. Kick the half over, be 7 pi over 18 plus pi over 2 is the same as 9 pi's over 18. So the set of solutions for this case would be x equals 7 pi's and 9 pi's would be 16 pi's over 18. 16 pi's over 18 is 8 pi's over 9. Plus 2 pi over 3n. And under this case, dividing both sides by 3, be 11 pi's over 18 plus 2 pi over 3n. Add the pi over 2, which is 9 pi's out of 18. and I get 20 pi out of 18, which is 10 pi out of 9. So there are my two solutions. Well, my two sets of infinite solutions for this particular function. So when you get to the problem sets for this, some of the questions do not have more than one answer. Some of them do. And the point of that is to have you think about which ones require two answers and which ones do not. So tread lightly. Good luck.